I'm Ivo. I'm a master student in Utrecht at the university there. And as part of my master, I've worked on the Helium compiler, which is a compiler for Haskell. So before I start, I would like to know if you have experience with Haskell. I've tried it before. Okay. Quite a lot. So for those who don't know, I will introduce Haskell quickly with some keywords. So it's a functional language, meaning that functions are first-class values. It's a pure language, meaning that functions cannot perform any side effects. So the only result of the function is the value which it returns. It of course has function expressions. It has pattern matching, polymorphism. We have type classes, which you may know as traits in Rust and protocols in Swift. For the backend, the most annoying feature is that we have lazy evaluation, which means that we only compute some expression if the value is really needed. And finally, we have partial application, also known as currying, and I will introduce that with an example. So consider you want to write a function which checks whether some number divides some other number. Then we can write it like this in Haskell. So we start by giving a type signature and saying that the function expects two integers and returns bool. And we can then write the implementation of the function by giving the two arguments on the left of the equal sign and an expression on the right. Now consider we want to write a function which checks whether some number is even. We can do that by partially applying the divides function. So we only give it the first argument, namely a, the value of 2, and we don't yet give the value of b. And this way we get a function which only expects that last argument. And that may become a bit more clear if you look at the desugared code. So when you desugar this code, you will see that divides is not a function taking two arguments, but it's in fact a function taking one argument and then returning another function which takes the second argument. When we then write divides 2, we're only applying that first function expression with argument a, and then just get a remaining function expecting argument b. So these features like polymorphism and partial application can make it harder to give good error messages. And that's also the main research topic for which we use the compiler in Utrecht. For instance, if you look at this piece of code, we were trying to write a list of bools, but we forgot to pass an argument to the divides function. And it's not a problem that we did not pass that argument, as it might be intentional to partially apply the divides function. But here we get a type error because we annotated the function saying that it's a list of bools, not a list of functions. So what a compiler does, if your program does not type check, it creates a type graph where the vertices denote type variables and the edges denote constraints between those types. And then we have some heuristics which decide which constraints should be removed to make the type graph consistent. And those constraints which are removed will be given as error messages to the user. And the compiler has a set of heuristics. For instance, in this case, we forgot to give an argument. There's a heuristic for that. Maybe you have swapped two arguments. There's a whole set of heuristics for that. But I won't go into detail about that, as this talk is about the backend. And for the backend, the most annoying feature, as I said, is the lazy evaluation of Haskell, which means that an expression is only computed if its value is really needed. To do so, we must create objects in memory which represent some computation. We call those Thunks, and we can use them to evaluate an expression later on. When we evaluate some expression, we only evaluate it to weak at normal form, which means that the start of the type is evaluated, or the start of the value, but not the whole value. So consider you're working with a list, which is represented as a singly linked list in Haskell. If you evaluate that to weak at normal form, then we only know whether that list is empty or non-empty. We do not know what kind of value is stored in the list or what the rest of the list looks like. The advantage of lazy evaluation is that you can write certain algorithms very nice. So for instance, we can construct a list which contains all primes. So we're constantly working with infinite lists here. So we start with a list starting at 2 to infinity. And we're finding all primes in that list. So you can, of course, not compute the length of this list. That computation would not terminate. But we can, for instance, take all primes less than 100, or the first 10 primes. The Helium compiler previously handled this with LVM, the lazy virtual machine. You should not confuse that with some other compiler framework which you might know. It had a stack-based instruction set, especially designed for functional languages, lazy functional languages, and that was interpreted. It had, however, some bugs, which made it hard to maintain, so we chose to implement a new backend based on LLVM. So the pipeline was as follows. We start with a Haskell file. At that level, we perform type checking. So we do not do any desugaring before type checking, such that we can give reliable error messages. Then we convert to core, which is a simple functional language. It's basically a lambda calculus with constructors and pattern matching. And then we go to LVM. The new backend, which we call Iridium. So Iridium is a strict imperative language. It does support laziness, but laziness is made explicit. We have SSA, and the control flow is similar to that of LLVM. So in fact, we could have been using MLIR. We have a functional type system, where functional means that it originates from a functional language, not that it works. We have pattern matching and some other high-level features. And we do support multi-parameter functions. So in Haskell, each function has only one argument, but we do support multi-parameter functions here for performance. So here's some sample function in Iridium. This is the null function, which takes a list and checks whether that list is empty or not. You can see on the first line that we have the same type system as the source level. So it says that it takes a list of A for some type A and then returns a bool. And in the entry block, you can see that we pattern match on the argument of the function and check whether it's an empty list or a non-empty list. And then we return either true or false. For laziness, we use Thunks, which is an object representing a computation or a partial application. So as we support multi-parameter functions, we may also have partially applications of those functions. Such object contains, a thunk contains a pointer to a function or to another thunk, the number of given arguments, and the number of remaining arguments. And that field is also used to store some magic number to denote some special state of the thunk. And finally, we store the real arguments of the function call. So if, for instance, we have a function which takes 3 arguments, and we partially apply that with 2 arguments, then we create a thunk containing those 2 arguments. If you then would later on apply that thunk with another argument, so the 3rd argument, then we create a new thunk pointing at that previous thunk with a last argument. The evaluation of a thunk is as follows. We first check whether remaining is 0, so if all arguments were passed. Then we mark that the thunk is being evaluated by writing some special value to that field. Next, we call the function pointer. And if it would then happen that during the call to that function, we're actually, again, needing the value of that thunk, we can detect that we got into a loop and throw an error. After the function call, we write back the value to that thunk, such that we assure that an expression is only computed once. So you may see that laziness is rather expensive. So we're constantly working with function pointers, and LLVM cannot optimize that. Plus, it's very bad for the memory usage, as we delay computation until maybe all of its arguments are out of the cache. So it's rather expensive. And another limitation is that a thunk may only point directly or indirectly at a function. Thus, we must assure that all expressions which may be computed lazily are actually function calls. So those are 2 things for which we will pay extra attention when we go through the pipeline of the compiler. So the pipeline, it started with Haskell, but we don't do any desugaring in Haskell. Then we go to core. Core is adapted from the old LLVM backend. The major change that we made is that we added a type system to core. Core was previously untyped, and now we have a type system. And after core we go to Iridium, and Iridium is compiled to LLVM. The first pass in core is the rename pass, which will ensure that all variable names are unique. That's not that special, so let's go to the second pass, which is saturate. This is pass which you do for correctness. So just like functions, we can also partially apply constructors. So here on the first line, we declare a function or a constructor foo, which takes 3 arguments, and then we only apply it with 2 arguments. So that code is transformed to a function expression, which takes that remaining argument and applies it to foo. And that way the constructor application is saturated. It does provide all arguments. The next pass is let sorting, which is a pass which we do for optimization. So in the compiler we have 3 kinds of let declarations. The first kind is a recursive let declaration, which means that the declarations on the right hand side may use the variables which are declared on the left hand side. So you can see here that the declaration for variable b actually uses variable c, which is declared in the same block. Furthermore, c uses variable b. So there's actually some kind of cyclic dependency. And because of laziness, this may work, depending, of course, on the definitions of f and g. However, you can see that a doesn't have to be in the same block. So what this pass does, it tries to minimize the sizes of the let declarations. And in this case, we can first create a block which declares variables b and c, and then create a block which declares variable a. You can also see that a, the expression for a, does not use the variables on the left-hand side. So we can change the declaration from a recursive let declaration to a non-recursive let declaration. And later passes in the pipeline only work on non-recursive let declarations, so this will enable other optimizations. The next pass is let inline, and that is one of the passes which only works on non-recursive let declarations. So what this pass does, it tries to inline the declarations of lazy let bindings. So in this case, we bind some value to x, and we may want to try to inline that. In this case, it may not be sound, as we're actually duplicating the call to f. And the semantics say that each expression is only computed once. So we have a few rules which say that if one of those applies, then we may perform the inlining. The first rule is if the definition of the variable is an unsaturated call, so a partially application, then we can inline it, as we do not use the sharing, as there's nothing we compute. So in the worst case, we may perform some additional allocations, but in many other cases, we are actually doing less allocation, as we may change a partially application to a full application, to a saturated call. The second rule is if the result of the thunk is not shared. So if you can, based on the AST, derive that the variable is only used once, or if it's used multiple times but in different branches of the execution, then we do not use the sharing and we may inline it. And the last rule is if the variable is not used, and that may not sound as inlining, but we inline it to all of its uses, namely none. It's mainly because it was easy to implement it in this pass. The next pass is the normalization pass. This pass is important for the correctness and the compilation to Iridium. What we do here is we assure that all sub-expressions are variables. So in the slides I have quotes around most, as we do allow arbitrary sub-expressions on some locations, but I didn't want to get into detail about that. So in this case we have a function call to f by applying another function call. And what we do is we bind that function call to a new variable, a z in this case, and then apply f with z. This will also allow that we can, in later passes, identify each expression with a name, which makes some analysis easier. One of those analyses is the strictness analysis, which is very important for the performance of the program. So as I said before, laziness is very expensive. So what this pass does, it tries to analyze which expressions will always be used during the execution of a program. If we find such information, we can evaluate an expression eagerly or strict. So if we know that function f always uses its first argument, we can compute g of y before calling f, and thus we can prevent that we allocate the thunk and get all the penalties of that. As you may see, this can change the behavior of the program, but that's not a problem, as the order of execution is not specified for Haskell programs. It's only specified which expressions are computed. So if you have, for instance, the example I showed here, error is a special function in Haskell which takes a string and reports an error. Then in this case you do not know whether you get error A or error B, as you need to compute both of these expressions, and it's not specified which of them occur first. The next pass is removedalias, which is a simple optimization. It tries to remove aliasing of variables. So in the top example, there is an aliasing of the form x is y. And in the bottom example, there's a similar example, but then with strictness. So we do this both for lazy let declaration and strict let declarations. So the exclamation mark denotes that an expression is evaluated strict or eagerly. We can only inline if the right-hand side was already strict, as we would otherwise lose some strictness information. Then we have a rather simple pass called reducedthunks, which will try to reduce the number of thunks that we create by eagerly evaluating some very cheap expressions, like a literal or a constructor. There's not much sense in putting them in a thunk. Then we have the pass lift, which is important for the correctness, for the compilation to Iridium. So in Iridium, we can only have thunks. In Iridium, we only allow arguments on the top level. So what we must assure is that all function expressions are also on the top level of a declaration. So if you find some function expression which is not on the top level, like in this case, where we have the lambda with argument z at the end of the first line, then we must lift that to a new declaration, declaration C in this case, where we bind that lambda with all variables which are in scope. Furthermore, we can only create thunks pointing at function calls. So if you find a lazy let declaration where the expression is not a function call, we will create a new top-level declaration where we add all variables which are in scope and the variable that we bound in that lazy let declaration. You can see that's happening with expr, which is some non-trivial expression which we lift to declaration B. So now we're in a specific form of the functional language, namely all arguments are on the top level, so all function expressions, and everything which needs to be put into a thunk is a function call. That means that we can convert to Iridium. So I'll start by giving some of the instructions in Iridium. We have let instruction, which computes some expression eagerly and binds it to a variable. And expressions can be calls, find nodes, eval, which evaluates the thunk to weaker normal form, literals. We have let alloc, which allocates thunks or constructors. And this may also be recursive, so we can handle laziness and recursive let declarations with this statement. Match and case are used for pattern matching. So case is the conditional jump from pattern matching, and match extracts the fields from an object. So those are the most important instructions. Then the pipeline of Iridium is as follows. We first have a pass thunk arity, which will ensure that we do not oversaturate calls in a thunk. So we could have passed too many arguments to a thunk. And what we will then do is we create two thunks, where the first one contains all required arguments, and the second one contains the remaining arguments. The next pass is dead code, which is an optimization. You will simply remove all dead code and dead variables. So all dependencies between statements are explicit by the variables that they use, as functions cannot perform any side effects. So we can do some aggressive dead code elimination here. Then we have tail recursion, which will convert tail recursive functions into a loop. You could say that this is an optimization pass, but you can also say that this is for correctness, as Haskell programmers usually expect that there is some support for tail recursion. And next, what we would like to do is do some memory management here. So we designed Iridium as an imperative language with a functional type system, such that we can do some low-level optimization at the end of the pipeline, while in an imperative language. So if you would do those optimization in a functional language, you're farther away from what's really executing. So things like memory management can be done at the end of the pipeline, and that's also the topic of my master thesis. So that was the pipeline in our compiler. At this stage we go to LLVM, which will hopefully optimize the program further. So the important passes for correctness are the normalization pass and the lifting pass, which will ensure that we can go to Iridium. And for performance, the most important pass is normalize, but that pass is helped a lot by passes like let sort, let inline. Before I conclude this talk, I would like to say that it's not only my work. There are a lot of master students and PhD students who have worked on or are still working on this project under the supervision of Julian Hagen. And I think that was all I had to say about the compiler. Do you have any questions?
Hi, thanks for the talk. It's very interesting. When you analyze for whether things are strict or not, is that sort of a optimal analysis? Will it catch all?
What analysis?
When you determine whether expressions are strict or not, whether that basically identify all the strict cases, or is it a heuristic?
So it's currently a rather simple analysis. Though there was a master student who did a master thesis on that, on creating a higher ranked strictness analysis. So currently there is a simple analysis which does not take the functional aspects in mind. So it basically only works with direct calls to a function. But using a type and effect system, I don't know if that's something familiar for you. A type and effect system. So a type and effect system means that you take the existing type system of a language, so a functional type system in this case, and then you annotate that type system with some analysis values. So for functions, you would then annotate whether they are strict in their argument or not. So that has been done, but it hasn't been implemented in the current compiler. So we know how to do it, but it hasn't been implemented. And you can take the precision very high, something which GC does not do. GC is the industry standard compiler for Haskell. But that research project did take it higher than GC, but it's currently not implemented in the current compiler.
Thanks for the talk. So regarding the thunk, do you think there is a security concern on that part?
On what did you say?
Security concern, because you say thunk is basically somehow stub functions which contain codes, right?
So yeah, could you elaborate a bit on how that could be a security problem?
Yeah, because normally you will, maybe I missed something in the thunk, but normally we will try to avoid or using some mitigation to like generate code and put it in the memories, because it provides more opportunity for the attacker to like jump to the points and execute arbitrary code or something, or like some rope attack.
Yeah, so if everything goes well, then so at the creation of a thunk, it points at a function pointer. So it should remain pointing at that. But yeah, we didn't verify the backend or something like that. So we cannot really give any guarantees about that.
Thank you for the talk. Very simple question. Maybe you explained that, but it was not clear for me. In your backend, what kind of code do you generate? Do you generate LLVM code? Is it IR code?
Yeah, we generate
code?
LLVM code.
IR?
So the compiler is written in Haskell, and there is a project called LLVM-HS, which has bindings to the LLVM API. But you have two variants how you can use that. Namely, you can use the pure Haskell implementation, which only has a pretty printer. And so then you can emit a text format, which is then passed to Clang. That's what we currently do. But we do get a statically typed AST, so that's nice. But there's also a binding to the LLVM library. But that currently causes that you cannot use GHCI, which is the interpreter of GHC. And we really need to use the interpreter because the compiler is quite large, and otherwise it would take a lot of time before you can test your code. So we currently must use that textual format, but given that we're using that project, we can just switch later on.
Thank you. And do you have some figures about the performance of your compiler?
No, sadly not yet. So there are definitely some optimization missing. And the major thing that's problematic to do real benchmark is that we do not have a garbage collector yet. So you're limited in the size of programs which you can run. So I hope that I can change that a bit with my master thesis. So we did run the Fibonacci function. And what's mainly problematic now is that we do not have inlining for type classes. But if you would perform such operation manually, we get similar performance to C. So it does show that the new backend has potential to be to have good performance, but there are just some passes missing.
Okay. Thank you very much, Ivo. Thank you for all the questions.